now that we've seen some of the results of the special theory of relativity in terms of measuring time, more specifically time dilation, the time dilation effect, let's turn now to measuring length and see what we can find out about that, especially measuring length of a moving object. And so here's our situation. We've got Alice and Bob again. Here is Alice. She is stationary. This is her ship or just some platform or something. We're just going to focus on one clock of hers for this example. And then here's Bob on his spaceship going by at some velocity v. We've drawn a number of clocks for him just to remind ourselves that actually in all the things we're doing, we always have that lattice or grid of clocks all synchronized. So in Bob or Alice's frame of reference. So all Bob's clocks are synchronized. He thinks they're in good working order. Alice, we're just showing one clock for her, but she'd have a whole lattice of clocks as well, and they would be synchronized for her. So, but remember, of course, as we showed earlier, Alice would not see Bob's clock synchronized and the other way around. So that will be a key point here in a few minutes. But let's get back to the example. So Bob's going to fly by here at some velocity v, and Alice is going to measure the length of Bob's ship as he goes by. And so to do that, when the front of his ship reaches her clock here, she'll take a photograph. It's our photograph principle again. And she'll see the time on her clock. We'll call that T sub A1. In other words, Alice's clock, time 1. And the photograph will also include the time on Bob's leading clock here, TB1. TA1 and TB1. And then that's the first snapshot. Bob's spaceship travels on. And then when the end of Bob's spaceship reaches that point, another photograph will be taken. By that time, Alice's clock will be at T sub A2, okay, her clock at time 2. And Bob's clock will have some TB2 on it as well, time T, B, number 2 there. So, how then does Alice get the result for the length of Bob's ship? Well, it's simply, we know that it's going to be essentially the distance traveled here. We know Bob is traveling at a constant velocity v. That's what Alice sees him doing. He will travel a certain distance in that amount of time, represented by essentially the end of her ship coming to this point here. And so that will be the length of his ship as, start the clock here, wait until you see the end of the ship go by, stop the clock as we did right here in our second snapshot. So TA2 there, and it's very simply, you take the velocity of the ship and multiply by the elapsed time between the time you see the beginning of the ship, the front of the ship, and the back end of the ship. So Alice will say, okay, I've got a result. And the result is the velocity times the time difference, T sub A2 minus T sub A1, just the elapsed time between those 2 points on her clock. So T sub A2 minus T sub A1. And we'll just rewrite that as we've done before using delta. So this becomes V delta T sub A, the elapsed time on Alice's clock. And then Bob says, well, I can also get the length of my ship from our little experiment here because I've recorded, the photographs record TB1 and TB2. So that's my elapsed time in terms of my clocks. I know I'm going at a velocity v, or really, you could think of it from his perspective as he could imagine he's at rest and Alice is going by. So he measures when Alice is at the front of his ship, TB1, and how long it takes Alice to get to the back of his ship at TB2. He's going with velocity v this way if he thinks he's at rest, and Alice clearly is going with velocity v that way. And therefore, again, the length of his ship is going to be v, the velocity, times the elapsed time on his clocks, TB2 minus TB1. So TB2 minus TB1. And again, we'll just rewrite that using our delta symbol. So it's V delta TB. And they get back together again, and they compare results. And Bob says, hey, you didn't get the same length as I did. What's going on here? You screwed up, right? Right? Why did you mess up your result? Well, as Bob considers it, he says, hey, you know what, Alice? Your clock is running slow. You know, my clock is in perfect working order. We have identical clocks. But remember, from our time dilation effect, moving clocks run slow. And so from Bob's perspective, he's at rest. Alice is actually moving that way compared to him. And he compares the ticking of her clock to the ticking of his clocks, the elapsed time. He says, Alice, your clock is off. Now, I'm sorry to say that, but your clock is off. That's why you're getting the wrong answer here. And my answer is correct. That, whatever the numbers we could put in, v times delta t sub b. And obviously we're assuming v is fairly close to the speed of light to get any effects here, as we shall see. But so that's what Bob is saying. Bob's saying, hey, my answer is right. You got the wrong answer, Alice, because your clock is not in working order. It's running too slowly compared to my standard clocks, which are in perfect working order. Well, what's Alice's response to that? And actually, a few minutes ago, we hinted at that. So you might want to think about a minute from Alice's perspective, what's going on? What does she point to in terms of Bob's measurement of the system, where she says, it's not my problem, Bob. You're the one who messed this up. So think about that a minute. If you want it, you can pause and puzzle that one over a minute. But here's the answer. The answer is that, remember our little phrase we used when we did an analysis like this with moving clocks, especially on spaceships? Leading clocks lag. Remember that? Leading clocks. Leading clocks lag. So as Alice looks at Bob's clocks here, if she were to look at all of Bob's clocks at the same instant, so say at this instant in time, we not only take a photograph here, but we have another photographic device out here. Remember, we imagine Alice having a whole lattice of clocks, so we can take a photograph any place along that we want and compare times with other clocks and locations. So take a photograph. When this photograph here goes off, she'll take another photograph simultaneously here. What will she see on this clock of Bob's? Well, Bob's clocks are moving toward her like this, past her like this. As we showed previously, leading clocks lag. She will see this clock behind this clock here. And therefore, she'll say, Bob, your clocks aren't synchronized. Notice that in Bob's measurement, he has to use two clocks. Alice is only using one clock. Bob is passing by her like that. To measure his own length, Bob has to use this clock and that clock for the length of his spaceship. And Alice is saying, I'm sorry to say, Bob, but your front clock here is not synchronized with your back clock. In fact, it lags by a certain amount. So that when this clock here, when this photograph is taken, this clock is actually further on in time at that point. And that's why you got the wrong answer. My answer is correct. So, what's going on here more quantitatively? Okay, so both of them are complaining about the other's results. And basically, in a sense, they're both right. But again, it's the relativity of simultaneity in terms of synchronized clocks, the relativity of timekeeping with time dilation, which we'll get to here in just a second, and as we'll see, the relativity of measuring length when things are moving. So here are the two results we got. Okay, Alice is getting this result, Bob is getting this result. They would turn out to be different answers if we looked at them. And the reason they're getting different answers we just explained. Again, Bob is saying, hey, Alice, your clock is running too slow. And Alice is saying, Bob, your clocks aren't even synchronized, so why even bothering to make these measurements? So let's look at these results a little bit further, because we now can apply. And, let's see where we're going to do this. Let's just remind ourselves up here for a second. Remember our time dilation result. And our time dilation result, from Bob's perspective now, he would say, in the elapsed time for Alice is 1 over gamma his elapsed time. Because from his perspective, so for Bob, From his perspective, Alice is moving. So let's start with that. So as he analyzes Alice's result here, I guess we will need some more room here. So you have the pictures in I forgot to mention, but it should be obvious. The handout has this diagram on that, so you don't have to redo it. In this case, we just have this one, or really two diagrams here. Not too bad to reproduce those. But let's look at then these results here. Okay, so we get LB. This is Alice's result for the length of Bob's ship. LB Alice, we said, was V delta TA. But Bob is saying, that delta TA, that time difference, is actually 1 over gamma delta TB. So this becomes V times 1 over gamma delta TB. In other words, remember, Bob says, Alice, your clock is running too slowly. Therefore, the elapsed time will be less. Remember, gamma is greater than 1. So from Bob's perspective, this is his explanation for why Alice's clock is running too slowly. It's running too slowly by a factor of 1 over gamma. So we put that in here. But look what we get from this. We just rearrange the terms. We'll have 1 over gamma in front. Let's put that in front and move the V over this way. V delta T B, but V delta TB is the length of Bob's ship from Bob's perspective. So this becomes 1 over gamma LB Bob. And now we have a nice little equation. So we'll write this down here. LB Alice equals 1 over gamma LB Bob. So now we have a nice little equation for measuring the length of a moving object in terms of the different lengths different observers will get. Bob gets a certain length LB for his ship, and as far as he's concerned, he's at rest. So he can just lay out his ruler there and measure it if he has to. Alice, though, as she sees Bob's ship flying by and trying to do the measurement with her clock and her knowledge of Bob's velocity, gets a result that's 1 over gamma Bob's result. Now remember, gamma is greater than 1 here, so her length is going to be less than Bob's length. Earlier we didn't specify that because we couldn't necessarily tell just from the results there which one was less and which one was more. We could see they were different. Could analyze that. But here's the quantitatively how they're different. That when Alice measures Bob's moving spaceship, the length of it, she'll get a result that's 1 over gamma times the length of whatever Bob gets just from being his own spaceship at rest as far as he's concerned. And note that we can actually see a similarity here between our time dilation equation and this is known as length contraction. Length contraction. In other words, moving lengths, if they're measured, contract. They're shorter than they would otherwise be by this 1 over gamma factor. So remember, before to get up gamma around 2, we have to get up to about 0.9, 0.99 speed of c, right around in there. Was it 0.9 c is 2.3 for gamma, something like that. So in other words, you have to get pretty close to the speed of light. But if you're going that fast, and so if Bob's going by that fast and Alice measures the length of his ship, it'd be about 1/2 of what he would get for that measurement. So let's write our two equations in general terms here because we've been using Alice and Bob with them. So let's do it like this. So we can say for the time dilation equation, we have delta t moving, okay? The elapsed time on a moving clock is 1 over gamma times delta t on a clock at rest. Okay, that's the so-called time dilation equation. Gamma being greater than 1, moving clock, the elapsed time on a moving clock is less than when it's compared to the elapsed time of an identical clock at rest. And then we can say, we'll say L moving equals 1 over gamma L, the length, a length at rest. So we're just transferring this, instead of saying L's above, we're saying moving and at rest here. So let's get rid of this in our analysis here, because we have a few more points to make with this. So this is the length contraction, so-called length contraction equation, so-called time dilation equation. Einstein actually wasn't the first to come up with these, as I think we've mentioned before. People like Hendrik Lorentz and Henri Poincaré were also coming up with similar results like this, but they were getting them in a very different fashion, and they almost seemed ad hoc results. They didn't seem to be coming out of the actual analysis. They sort of had to put it into their theory. Einstein is getting these results just from his two basic postulates, the principle of relativity, principle of light constancy. Put those together, and you discover that the speed of light is a constant, same value for all observers, no matter how you're moving with respect to speed of light. And then you started analyzing things like the light clock example and start getting these somewhat weird results here, that depending on how you're moving with respect to something, time, the elapsed time that you will measure, it will be different, and same thing with lengths as well. A little bit of terminology here. When we talk about, let's start with the length here first. The length at rest, in other words, if Bob is just sitting there in a ship, he's at rest as far as he's concerned. He's measuring his length of the ship. We call that sometimes the proper length. It's not the greatest term necessarily. In German, the German terminology for it, of course, which Einstein was using, he called, I believe, his own length, just, own length. I think my German is really rusty, but I think it's Eigen, I'm not sure now. Anyway, own length in English, I know that much. In other words, it's Bob's own length at rest as he measures his spaceship, or whatever he happens to be measuring. And proper length has connotations of, okay, if this is proper length, another length we might be talking about is improper, and that's not the case at all. So it's the length measured at rest. And same thing for time. We could talk about proper time, or sometimes rest time. So that is the time measured on a well-running clock at rest. Sometimes some people like to call it wristwatch time. It's the time you would measure on the watch on your wrist. It would be a different time if you saw somebody's watch flying by and you were able to measure that, as we've been analyzing. There would be the 1 over gamma difference in the two-time measurement of the times there. So some terminology there. One more question here. We actually asked this before when we talked about time dilation. Is this real? As Bob's ship goes by, what does Alice actually see? Right? Well, here's where we have to go back to the distinction we made early on in terms of observing something versus perhaps seeing something. And we defined observation using our photo principle. That an observation meant we had this imaginary grid or lattice of clocks, and at any given point we wanted to fix something, that something happened at that instant in time and space. We could take a photograph there, the clock would show it, all the clocks are synchronized in our frame, and we'd be able to specify the time and location in our frame of reference, and that's what we meant by observing something. The reason it's important is that if you talk about seeing something, then technically you have to think about, okay, if it's happening over there someplace, even though I have my grid of clocks and I can take a photograph out there and get the time, look at the photograph later, know what the time was and the location was. To see that actual event, I have to have light coming from it. Say it's a flash of light over there. I have to have the light coming from it back to my eyes, of course. There's a delay involved, and different things can happen if you have that delay, especially if you have an object moving past you. And involves an additional layer of complexity. It is possible to do that analysis, but it also gets a little confusing in terms of the basic concepts that we're trying to get across here. So these concepts are correct in terms of our analysis, and they're well supported experimentally. And if we talk about an observation being made in terms of our lattice of clocks and our photo principle, yes, it is absolutely true that a clock at rest will keep different time compared to a clock that you see moving along, and the length of something at rest will, if you put that in motion and then watch it go by, you will actually measure a different length for that. A little later on in the course, maybe almost the last week, next to last week or the last week, we'll look at this in a little more detail, because again, you can ask, do things really compress like that? If Bob is riding in his spaceship, does he sort of feel all of a sudden all sort of compressed? And you could also ask, well, what if there are multiple observers watching Bob, who maybe one of them is at rest, so he's going by at v, another one is going at half v, so he sees Bob at different velocity. Does Bob feel different types of length contraction? And the answer, of course, is no. Bob, as far as he's concerned, is at rest. And he doesn't feel any of this. It's the observations of other people making various determinations of the length that will depend on the relative velocity between them. But for now, we just have to focus on what we've got so far, our two big equations here, time dilation and length contraction. Again, elapsed time on a moving clock will be less than the elapsed time on an identical clock at rest by this 1 over gamma factor. And the measurement of a length will be less if you measure it while it's moving by the 1 over gamma factor versus if you measure it when you're at rest.